Well, I kind of messed up, and I didn't. We again don't have handouts for today. I actually, I didn't like the way last year the lecture was sort of presented in the second half, so I redid it the second half, and I haven't printed it out yet, so I just sent it to the printer. So we will just get started. There isn't really much to mark up in the first few slides. It's kind of just an informational thing. Yeah. Although actually, I think some of it's pretty much the same. Yeah, I pretty much just changed the beginning. I'm printing them out again, so I'm going to get started, and then I'll, once I get to an example problem, I'll run off and get a handout. So this is kind of just an overview. Were there any questions on homework 5 at all? Source transforms? Assignment or problem 417. This is homework 5. Oh yeah, that one. Yeah, you're supposed to use superposition. So it's to practice superposition. If you're doing the wrong technique when I grade it, you might get points off. Someone used nodal to solve that one diamond-shaped currents problem with all those 4 currents. That was a weird one on this. And you know, it's a chance you're supposed to be practicing mesh on homework 4. So, but you know, if it says use superposition, yes, you should use superposition to solve it. I'm not interested in getting the answer. I'm interested in that you're getting an understanding of what the technique is all about, right? That's the thing. So people are like, oh, I got the right answer, but maybe on a test that's okay. But on homework, I really want, you know, these are techniques that we're learning to kind of improve our understanding of how circuits work. So where all possible, you should do the technique that's listed and not try to do one that's easier. Sometimes there will be an easier way, but best not to do it. Any other questions on homework 5? Okay. So we're moving into Thevenen's theorem, and this is actually probably one of the more difficult parts of the class. So we're diving right into the lecture. We should get it done by Wednesday, and then we'll actually have 2 days of problem sessions if everything goes well, so that you can really work out the details of this thing. There's a lot of complexity to it. So what we learned last week was the ability to talk about equivalent circuits, that you could have a current source in parallel with a resistor have the same effect as a voltage source in series with a resistor. Thevenen's theorem takes it further and says any circuit, any linear circuit, and a linear circuit is a circuit that's composed of resistors, capacitors, inductors, op-amps, anything that's in the linear, it's in linear mode, that works in a linear fashion. If it's all linear, you can reduce that to a voltage source in series with a resistor. Well, that's kind of like what we were doing with source transform. So it's just really an explicit way of identifying what you can do with source transform. Norton's theorem is a parallel to that. It says any linear circuit can be reduced to a current source in parallel with a resistor. These two are source transforms with respect to each other. And if you came in late, I'm going to get a new copy of the handout. I forgot that I changed this thing. I put a note to myself here. Why? Why do we have to do this? Why? It's so hard. Because quite often when you're dealing with engineering systems, components, they just get so complicated. And if you really want to understand how things are working, you have to sort of reduce them to essential factors. So in statics, when you had a bracket that had 3 forces acting on it, maybe all you care about is trying to figure out, how much force is going to be on those bolts holding the bracket, and when you got those 3 cables attached to it. Well, it's cumbersome to think about those 3 forces separately. It's easier to combine them into a single force. And we learned how to do that so that you could take these 3 forces and reduce them to a single force applied at a particular angle. That's just vector addition that allows us to do that. If it was so easy for circuits, right? But in circuits, when you have multiple sources and resistors, you can reduce that as well to equivalent circuits containing only a single source and 1 resistor. So this whole mess of stuff here, if all you're interested about is what's happening at the load here, you can replace all this stuff with just this. So in the same thing here, if all we're interested, in this case, the bracket experiences the same force applied to it, no matter if it's 3 separate forces or 1 single force. In this situation, the load experiences the same current, or has the same. The load can't tell the difference. If you pull out this load here, you can't tell the difference whether you've got this complicated circuit here or this simpler circuit here. So we've succeeded in simplifying it so it makes it easier to understand what the load's going to be doing. So Thevenen's theorem says if you have a linear circuit of current sources, voltage sources, resistors, and you want to hook up a load to it, you can replace that with the Thevenen equivalent of that, whatever in that box, and you'll get the same net effect. You can replace any linear two-terminal circuit with an equivalent circuit consisting of a voltage source in series with a resistor. And the Thevenen voltage is the open circuit voltage. That means if you remove the load and just measure the open circuit at AB, that's the Thevenen voltage. That's V Thevenen. And R Thevenen is the equivalent resistance at the terminals with all the independent sources turned off. So that's one way to find the Thevenen resistance. You can just turn off all the independent sources and find the equivalent resistance from A to B. And that's what we're going to be doing that. And when you have an independent source, a voltage source turned off becomes what? You turn off a voltage source, what do you get? Oh, amazing question? Yeah, is that a unique answer? Yes, there's only one Thevenen equivalent circuit for a combination of components, yeah. So you boiling it down to one unique answer, right? Just like with the cables, there's only one unique resultant vector sum of those 3 vectors, right? So it's the same for circuits. Isaac? Well, you can make it a current source. That would be a Norton's equivalent circuit, yeah. And Norton came along later. I guess, these things are sort of named, I think, in honor of these people after they pass. I don't think, Norton pushed to have his name attached to a current source equivalent. I think it was just a convenient way. Let's just call that the Norton equivalent because Norton was a pretty cool engineer. So they're very similar. They're just source transforms of each other. So, but when you turn off a voltage source, what do you get? A short circuit, right? And when you turn off a current source, you get an open circuit. So we're going to do this example, which is on your handout, and maybe I have. But if I don't come back to this. So here's the situation, and we're asked in example 5 to find the Thevenen equivalent circuit with respect to terminals A and B. And having done that, you'll see that knowing what the Thevenen equivalent is, it's real easy to find out what the current is through the load resistor for a bunch of different values of RL. And this is one advantage of knowing what the Thevenen equivalent is. Once you do simplify the circuit, you can easily determine what the current is or the voltage is across RL as you vary RL. And that has advantages for certain situations. So we'll start with looking at the Thevenen resistance. So we're going to start by solving for R Thevenen of this circuit. And again, we're just looking at everything to the left of A and B. And what we do is redraw the circuit, but we turn off all of these sources. So that 32-volt source is off. It becomes a short. The 4-ohm resistor is there. The 12-ohm resistor is here. 2-amp source is off, so it's an open. And the 1-ohm is there. If you didn't like series and parallel circuits, you're not going to like Thevenen equivalents. You got to be able to kind of look at this thing and figure out what's in series and parallel. And everybody has sometimes different ways of thinking about this. And we're going to have to kind of just going to put that as a 1, get that cleared up here. So what is the effective resistance at the terminals AB of that circuit? Anybody? Pop quiz. Everybody give it a stab. Mark? Mark says 4. Okay. Mason. What is the effective resistance at the terminals A and B? So if you hook up an ohm meter right here to that network and you're measuring ohms, how many ohms is it going to read? 4. Why? Why 4? Pardon me? 4 and 12 are parallel. And that makes 3, and that's in series with a 1. Okay? This is, and so again, we're changing the, the V sources to become a short circuit. So the I source is becoming an open circuit. That's how you solve these. Now, if you're not clear on why it is that way, or maybe you thought it was something different, one way that I tell people to help explain this is you're driving on a long journey from A to B, and you're an electron or an imaginary positive charge. You're starting off your trip at A, and you're driving and driving, and the first thing you drive through is a 1-ohm resistor, right? And then what happens is, well, you have this detour, but the bridge is out, so you can't go that way, right? And you can keep on going, and then you run into a fork in the road, right? You have a choice. And some of the cars are going to go that way, some of the cars are going to go that way. That's a parallel branch, right? So you have to find the parallel resistance of that. And then whichever way you go, you're going to meet up here at this juncture, and everyone's going to go this way all the way to B. A lot of people, they kind of they look at the angle, the circuit from a different like starting point, and you can get a different answer if you're looking at it from a different point. It's always looking at it from A and B. So you should always imagine yourself driving from A to B and looking at the patterns of, what's in series and what's in parallel as you go on that pathway. Okay, well that's the Thevenen resistance. The Thevenen resistance is 4 parallel with 12 plus 1, which is 3 plus 1, which is 4 ohms. So that's actually pretty easy. The Thevenen voltage is the open circuit voltage at AB, right? So that's VOC, open circuit at AB. So we draw the circuit again. In this situation, we have the sources on. And we've got the 2 amp source. And what we're trying to find is this value here, VOC, which is our V Thevenen, our Thevenen voltage. No problem. Okay, so in terms of nodal, if we want to do a nodal analysis, we can make this bottom node the ground, and that means this whole thing is ground. And we know that this node here is 32 volts because we've got a 32 volt source attached to it, right? And then we can call this node here V Thevenen, right? Okay. And what are we going to call this node right here? You're solving the problem. You've circled the node. What are you going to call it? Sorry? Sorry? V2, node A, on? 24 volts? Well, you already solved it? Yeah. Well, before you start calling it 24 volts, there's a trick here that can make this easier for you. Rather than calling it V1 or VA, you should look at this resistor here. What was this resistor here? This is a 1 ohm resistor. And ask yourself, if there's an open circuit at A and B, how much current is flowing through that resistor? Isaac's shaking his head no. 0, right? Good. So if I equals 0, what's the voltage drop across the 1 ohm resistor? 0, right? So this is an example of what you would sort of call a dangling resistor, which has no voltage drop, right? I'm calling this a dangling resistor because it's dangling in space, right? Somebody remind me tomorrow to have you measure a dangling resistor voltage. You can just hook up a 12-volt source, put a resistor across it, and then your voltmeter, and measure that thing, and it's going to be the same as the voltage source, because you're not having any appreciable voltage drop when you have no current going through a resistor. So what can we call this node voltage? If there's no voltage drop across that 1 ohm resistor, what would be an easier, more convenient label for this node? All right, not 24 volts. VTH, right? It's the same as V Thevenen. And this is one of those little insights you have to have when you look at a circuit to keep the calculations from getting too complicated. If you call that something else, Maybe you'll eventually realize when you do KVL there that it, you know, or do your nodal thing there that it's the same, but you might not. You might actually write this. If you call that V1, you would say, oh, this current isn't 0, if this current is V7 minus V1 over 1 ohm. You know, you might say that, and that's sort of could lead you astray, right? Because it's the same thing, V7 and V7, both sides of the current is 0. So the nodal equation then is really just one to solve this. You have 32 minus V7 over 4. That's the current going into the V7 node from the left, right? Plus 0 minus V7 over 12 plus 2. You multiply by everything by 12, so you'll have 96 minus 3 V7. Minus V7 plus 24 equals 0. So that will tell you that V7 is 30 volts. Isaac? Even if the dangling resistor wasn't 1 ohm, what would you like it to be? Yeah, what if it was 1,000,000 ohms? How much current's going to be going through there? What if it was 0 ohms? What if it was just a wire sticking out? Current has nowhere to go. Has to have a return path. If you have a dangling thing just sticking out there, no way to have a return path, current has to be 0. So V7 is 30 volts. I hope you left enough room on the right side, because we're now going to answer the original question, which was, what's the current through RL if RL was 6, 16, and 36? If you didn't have Thevenin's theorem, David, question? Yeah, could you solve for the Thevenen equivalent using source transforms? You already did. You did that last week. Yes, you could. Yeah, that was basically homework 5. Source transforms are one way to find Thevenen equivalents. If you keep source transforming everything until you get to a single voltage source in series with a resistor, you're done. But if you have a dependent source, that may not be so simple. Yeah. So, but you can do a Thevenen's equivalent with dependent sources, but not using source transforms. Mason? This method, yeah. Well, this is the challenge with Thevenen is that there's a few different approaches to solving these under different circumstances. And we're going to be looking at the standard way, which is this way. When you just have independent sources, you can turn them all off and then just measure the equivalent resistance. That's pretty easy to find R Thevenen. And then V Thevenen is just finding that open circuit voltage, which is usually easier using nodal analysis. But again, why are we doing this? And the motivation for doing this is to gain an appreciation of what's going on in that network that you can't get just by keeping the original components there, right? If you know that V Thevenen is 30 volts and R Thevenen is 4 ohms, by the way, I kind of remember sometimes like we go through all these things to compute like the Thevenen equivalent circuit, and then like later on there'll be like a problem asking you to draw the Thevenen equivalent circuit, and like some people just don't seem to know what that is. The Thevenen equivalent circuit is that Thevenen voltage in series with the Thevenen resistance, right? So this is the Thevenen equivalent circuit. If I circle this, I just want to make sure you've seen it. This is the Thevenen equivalent of the network to the left of AB. In other words, the Thevenen equivalent of this. It's an equivalent circuit that has the same effect on the load as the original circuit. It's, everything to the left of AB. It's a Thevenen equivalent of everything to the left of AB. Okay, but like if you were going to go out into the field and you know, you had some complicated system, power system, you had to plug in different loads in there, and you wanted to sort of figure out what the load was going to experience before you plug it in. If you knew the Thevenen equivalent, it would be really simple to find the load current, right? The current going through the load is going to be I sub RL. And I sub RL is going to just be 30 over 4 plus RL. So with a pocket calculator, you can easily find the answer. If the load, if you put in a 6 ohm resistor, the current's going to be 3 amps. Right? If you put in a 16 ohm, it's going to be 1.5 amps. If you put in a 36, it's going to be 0.75 amps. Isaac? What is the notation RL? RL stands for the load resistor. Yeah. That's the current. This current? Yeah, that arrow there is current. What diagonal one? Oh, this. Yeah, this just means it's a variable resistor. And we have one of those in our circuit kit. It's a blue plastic box that has a knob on it. Actually, there's a few different ones, but ours, I think, looks like this. And as you rotate the knob, you get a different resistance between 2 of those pins. It actually has 3 wires on it, but it allows you to change the resistance, which is really good for like tuning circuits to do things. Yeah, and you know, it gives you some flexibility in how you. Sometimes it's really convenient to have a variable resistor in your circuit. Okay, that's the plain old one, right? So this is the Thevenen equivalent with independent sources. And you might go back here and just, this is sort of the technique for when a circuit only has independent sources. When you only have independent sources, this is the technique, the main technique you'd want to use. It's pretty straightforward. When you have circuits with dependent sources, it's a little tricky. The Thevenen voltage is still the open circuit voltage at the terminals, just like last time. But the Thevenen resistance is the resistance at terminals with all the independent sources turned off. You still have to leave the dependent sources on. And finding our Thevenen means that you turn off all the independent sources and you apply either a test voltage source or a test current source at the output, and you figure out what's the what is the other one, and it's more convenient to just use a test voltage or test current with a value of 1. You're just hooking up a source to the output. And what are you guys looking at? I bet it's not a circuit. So the idea is, just suppose this is, say, for example, 1 volt. You could do a different one if it seems like it would be helpful. And the idea is that, you know, suppose you have this circuit and you've turned off all the sources that are independent, but you just have a bunch of diamond dependent sources in there. And the point is, you have to figure out what is the Thevenen resistance of this circuit at those terminals. And that's not so straightforward. And what I mean by hooking up a test source is you are connecting something here. Instead of a load, you're connecting your very own source at this point right here. And it's going to have a voltage source of voltage of V0, and you can call it a voltage source and find I0, or you can call it a current source and find V0. And when you find that, the Thevenen resistance is just that test voltage source VO divided by IO. See, because the thing is, when you apply a source to that output, it's going to activate those dependent sources. Those things could potentially come on, and then they could kick back, or they could draw more current from you. So you can actually have things like, you can actually get like a negative Thevenen resistance if, like, when you apply some voltage to it, it starts spitting current back out at you because the dependent source kicks on and starts spitting current back, right? If it was just a passive resistive thing, I0 would be positive, but if these dependent sources kick on, they could flush current out, in which case you have a negative resistance, which seems kind of odd, but it is possible to be negative. If you only have independent sources, it can only be positive. And I remember, like, I think the whole one time, the whole class, I don't think they ever had a negative Thevenen resistance except like on the test. So don't freak out if it happens. You have a negative Thevenen. It could be correct. So again, the equivalent of that is you're still able to reduce this, even with the dependent sources, you're still able to reduce this to well, here's a circuit that doesn't have any independent sources. And when there's no independent sources, the Thevenen voltage is 0. But it's like you are reducing that whole thing to a single resistor, even though it has dependent sources inside there. So the R Thevenen equals VO over IO. Okay, so now we're going to do a dependent source problem. Here's a circuit that has a dependent source. And in this case, we'll just start off by doing V Thevenen first, right? So to find V Thevenen, we're going to still have to find the open circuit voltage, right? So this open circuit voltage is our V Thevenen. That's whatever that thing is when there's no load applied to it at the terminals is your Thevenen voltage. So that means if we're doing nodal analysis, right, we're going to call this node the bottom node, the reference node. And we're going to call this node here V Thevenen. See if you remember my advice last time, right? So what are we going to call the node here right above the 6 ohm resistor? V Thevenen, yes. Right, you're learning, right? That's the trick, right? It's less unknowns, right? Why can you do that? You have a tangent resistor, and therefore there's no current going through it, so there's no change in voltage across that resistor. Isaac. It does. OC stands for Orange County. Open circuit. Yeah. And SC stands for short circuit. Yeah, I'm going to be using those a lot. Okay. And so this is Thevenen. We actually have, well, what are we going to call this node here? Another trick question. What are we going to call that node? VF? Vx. Why Vx? Because Vx is the voltage across the 4 ohm resistor. That means you're hooking up a voltmeter there, so that's Vx. So you see how we have the minimal number of unknowns? We'd really just have Vx and Thevenen, 2 unknowns in that circuit. So what else do we have in this circuit that makes it interesting? You're going to do nodal analysis. What do you see? Mark. You see a supernode. Do you all see it? Where's the supernode? At the top, right? This part right here is a supernode. Why is it a supernode? Well, there's a voltage source. Well, there's no. Yeah. Is it any old voltage source? What about this that makes it a supernode? Sorry? A dependent voltage source. But that doesn't necessarily make it a supernode. What makes it a supernode? It's floating. What does floating mean, Isaac? It's in between 2 nodes. 2 what kind of nodes? 2 nodes that are not the reference node. Okay. So this is floating. Oops, not that. This is the supernode. This is a floating voltage source. Why is the 2 ohm resistor included? Well, you don't have to, but the current leaving the supernode going one way into the 2 ohm resistor is going to be the same as the current entering the supernode. So it just sort of cancels out. You're welcome to include it. It's just going to cancel right out in your first equation. And I can show you that if you want me to show you. Floating voltage source means neither side connects to the reference node. If it did connect to the reference node, then you would know what the node voltage was on the other end, right? So, so some people tend to kind of forget that. A floating voltage source is neither side connects to the grounds. So the supernode equation for Vx and Thevenen says, well, let's see, we've got the current entering, right? We've got 5 amps entering. You've got 0 minus Vx over 4 entering, right? Plus, that's this current, you got 0 minus Thevenen over 6. And Isaac, what's the last current? Well, there isn't one because this current here through the 2 ohm is 0. But if we wanted to do these, suppose Isaac wanted to know, do we have to include the 2 ohm? If you didn't include that in there, right, then you'd have to actually have the current, you'd have to define the current going this way into the supernode plus the current going that way into the supernode, which just cancels out. You know, you'd have to say Thevenen minus Vx over 2 plus Vx minus Thevenen over 2. You know what I'm saying? So therefore, it cancels out. So why not just include that in the circle, and then you don't have to include that in the equation, right? No, actually, why don't you do the by inspection equation since you asked? That sounds good to me, right? Everyone agree? VTH minus Vx equals 2Vx. What up to the 2 ohm resistor? Well, it doesn't matter because we're talking about voltage potentials. This is just enforcing a potential difference between these two nodes of 2Vx. And that difference is also V7 minus Vx. Yeah. Yeah, if you want to find the voltage drop across the 2 ohm resistor, it is V7 minus Vx. And so the current is V7 minus Vx over 2 going to the left. That's right. 2Vx over 2 ohms would be that current. Amazing. Yeah. And a little bit work says that 3 V-Thevenins then would have to equal Vx. So Vx is equal to 3 V-Thevenins. Wait, I did it the wrong way? Sorry, I did it the wrong way. V7 equals 3 Vx. So I could multiply, well, let's see. Oh yeah, so this becomes 5 amps minus Vx over 4. But then if we have V7 is 3 Vx, then we have a minus Vx over 2, right? Which I could then multiply by 4. And it will turn out that Vx equals 20 over 3. Therefore, whoops, V-Thevenin equals 20. You can read that, that's a 20. Okay, 20 volts. So in our quest to find the Thevenen equivalent, first of all, what am I drawing right here? What is this? What is that? That's the Thevenen equivalent circuit, right? If you're asked to draw the Thevenen equivalent circuit, that's what you have to draw. And we just found out that the V-Thevenin is 20 volts. So it's just the Thevenen voltage, the Thevenen resistance arranged in a little circuit like that. And we are now going to find what is our Thevenen. So we turn off all independent sources. And what does our circuit look like when we do that? Well, the 5 amp source gets turned off, and that'll leave some room here. But we still have this dependent source here that's 2Vx, Vx being the voltage across the 4 ohm resistor, or the node voltage right here, right? And we have the circuit there. So it has one dependent source, and it has a couple nodes there, a couple terminals here, A and B. And at A and B, we're going to connect now a source here. And in this case, we're going to choose an I/O of 1 amp. Why is that better than a voltage source? Well, if you're doing nodal analysis, it'd kind of be nice to know that that current going through that 2 ohm resistor is exactly 1 amp. So that can help. And we're going to call the voltage at AB, we're going to call that VO. The B is getting a little closer, so I'm going to move it down below. And so if we're putting in a 1 amp there, the question is, what is VO? And again, we have that supernode deal. So the supernode says, well, we still have this constraint, right? That 2Vx has to be this node minus that node. So this node really still has to be 3Vx here, don't you agree? Right, because 3Vx minus Vx is still going to be 2Vx. That still has to stay the same for that dependent source to work right. So that's 3Vx right there. So we can just do the supernode by saying, all right, well, we have to do the whole equation again, but that node still is 3Vx. The supernode says that 0 minus Vx over 4 plus 0 minus 3Vx over 6 plus 1 amp equals 0. So you see why it was nice to do a 1 amp source there? That kind of helps. So that means our Vx, doing a little bit of algebra there, would be 4/3 of a volt. And then we can write the current for the current going through that 2 ohm resistor, which is 1 amp, right? And so, 1 amp equals VO minus Vx over 2. And so therefore, that's going to tell us that VO equals 6 volts. So the R Thevenin, what's the Thevenin resistance of that circuit then? Six ohms. So what it's saying is the equivalent circuit of this complicated thing with a dependent, independent source and 4 resistors can be boiled down to a single voltage source of 20 volts in series with a 6 ohm resistor. That embeds the property of the dependent source reacting to whatever thing's going on there. It allows you to model, if you want to hook up a load there, it allows you to attach a load and figure out what's the current going to be for different resistance values. Mason? Y is 1 amp equal to V naught minus Vx over 2. That's a nodal, that's the way we do an equation for a resistor. If we know this node here is VO at A, that the node voltage here is VO. So VO minus, it should be VO minus 3Vx, sorry. Thank you for catching that. VO minus 3Vx over 2. Now, you didn't have to use a 1 amp current source. Tomorrow or Wednesday, we'll do this whole thing for the Thevenin resistance with a 1 volt voltage source at VO and find the current, and you'll get the same answer. Isaac, and then Matthew. Were you assuming that IO is 1, or did you find that somewhere? No, you just arbitrarily selected. It's just like, okay, you're coming up on a bench, okay? Let me just sort of, imagine you're coming up on a bench and there's this gobbledygook circuit here, and you turn off the power, or even better, you've got some weird box which has 2 terminals coming out of it called A and B, and a power switch, and you turn the switch to off, and if you happen to have a handy dandy current source in your back pocket, you're just hooking up a current source to it, and you're sending in 1 amp into the A terminal, and then you're measuring what's the voltage across this thing. Whatever is in there, it'll tell you the Thevenin resistance of that thing. Just take the voltage that you end up getting at those terminals, divide by 1 amp. Yeah, 1 kind of makes sense. It could be anything if for some reason you want to do something else. you'll still get the same answer. It's linear, so if you made it a 2 amp, then your Vx would be 8/3. So you still get the same answer for VO. Or your VO would be 12 anyway. Matthew, do you have a question?
Yeah. When you make a supernode equation, when we're trying to find what the Thevenen resistance is,
Yeah.
can we just take that straight from 4?
Well, here's what. Yeah, the question is, did we just take that solution from the previous one when we did the R Thevenen and use that 3Vx there? Not really. And one thing I really have to enforce, because some people will like, the work that they did for the open circuit voltage, they'll use some of the numbers. They're like, oh, V Thevenen is 20 volts, so then therefore, the current there is just 20 minus 3Vx over 2. But the V Thevenen only works, when it's an open circuit there. So it just happens though that this dependent source, because it enforces, it wants to have 2 Vx voltage drop between its 2 terminals, and we have Vx on the bottom terminal, then the top terminal still has to be 3Vx, because 3Vx minus Vx is going to get you 2Vx. It's a property more of the dependent source that hasn't changed, rather than any of your analysis from the previous section. You know what I mean? Yeah, it's unfortunate, but people make that kind of mistake. Even though I say it, people are still going to do it because you got to practice this stuff, and over and over and over again. That's why we're going to have 2 days of practice this week. And Hong's going to do all the error checking for everybody. You're going to check everyone's errors. Please. Maybe I will find some funding for you to grade everybody's work.